Hi, my name is Travis Rao, and I will be talking about degree versus approximate degree and quantum implications of Huang's sensitivity theorem. This is based on joint work with Scott Aronson, Shalov Ben David, Robin Kothari, and Abhishek Tal. I also want to give a shout out to Huang. Huang came out with this breakthrough proof of the sensitivity theorem a couple of years ago. And the results of this talk sort of rely on Huang's proof of the sensitivity theorem in a pretty crucial way. So even though Huang isn't a co-author of this paper, none of the results in this paper would really be possible without his work. Cool. So I'll start by giving a brief summary of results. I'll use a lot of terminology that I'll define in later slides, but I want to just start by giving a brief overview of how this talk will go. So the subject of this work is going to be Boolean functions. Right, so these are functions that take in a string of, say, zeros and ones and output a 0 and a 1. It's going to be really important in this work that our functions are total. In particular, a lot of the results we prove don't really necessarily apply in the case that our functions are not total. Right? So in particular, a function is total if, for every single input, there is an output. Cool. So we have two sets of results in this work. The first is that the degree of a function is bounded above by the quantum query complexity of that function squared. This has two consequences. The first is that the degree of a function is bounded above by the quantum query complexity of a function to the fourth power. The second consequence is that the quantum query complexity of any non-trivial monotone graph property on n vertices is omega of n. So this is a resolution of the quantum version of the Aanderaa-Karp-Rosenberg conjecture. The second set of results starts with the relationship between the degree of a function and the approximate degree of a function. In particular, we show that the degree of a function is bounded above by the approximate degree of that function squared. One consequence of this is that the approximate degree of any read-once formula on n variables is omega of square root of n. Cool. So as I mentioned, sort of the main subject of this talk is going to be Boolean functions. And it will be helpful to have a couple sort of running examples of Boolean functions just to sort of contextualize a lot of these definitions. So we'll use the examples of dictator, or, and XOR. So the dictator function sort of looks at the input, only looks at the first input bit and outputs that bit. Right? So it only outputs that first bit of the input. You can think of the first input bit as sort of dictating the output of the function. Or is a function that 0 of all the input bits are 0 and is 1 otherwise. Another way you can think about or is that you're kind of searching for a 1 in the input. And if there is a 1, you output a 1. If there is no 1, you output a 0. Finally, in XOR, the way XOR operates is that it adds up all of the input bits. If the resulting sum is even and outputs 0, the resulting sum is 1 and is odd and outputs 1. So the first notion I'll define is that of deterministic query complexity. The deterministic query complexity of a Boolean function is the number of deterministic queries, and it's worth mentioning that these can be adaptive, that are required to compute f on any input. So you can think of this as trying to compute f of x by reading as few bits as possible. So we can try to figure out, what is the deterministic query complexity of these three examples I mentioned at the previous slide. The deterministic query complexity of the dictator function is going to be 1 because all we need to do is check that first input bit, and that will give us the value of the dictator function. The deterministic query complexity of XOR is going to be n because no matter how we choose the first n-1 input bits to read, that last bit is going to determine the value of our function. So, and for XOR, it's necessary that we look at all n input bits. Finally, the situation with OR is a little bit more complicated. As soon as we see a 1 in the input, we can output a 1. But it could be the case that, if we're unlucky, if the first n-1 bits that we read are all 0, in which case that last bit will still determine the output of our function. So in this case, the deterministic query complexity of our function of OR is going to be n. The next notion I'll talk about is that of quantum query complexity. The quantum query complexity of a Boolean function is the number of quantum queries required to compute that function on any input. And this case will allow an error probability of at most 1/3. Cool. So we'll have a quantum state. We can apply a unitary independent of our function. Then we can apply a quantum query operator, then another unitary, and so on and so forth. And finally, we can perform a measurement. Again, we can ask ourselves, what is the quantum query complexity of these example Boolean functions that we have? In the case of the dictator, it's going to be the same as the deterministic query complexity is going to be 1. With XOR, you can do a little bit better than n queries. In the quantum query complexity setting, you can compute XOR with n over 2 quantum queries. With OR, you can do significantly better. With OR, you can compute OR with about theta of square root of n. Quantum queries, the one algorithm that does this is Grover's algorithm, which sort of searches for 1 in the input. Cool, and sort of one of the big questions we can ask is, what is the relationship between deterministic query complexity and quantum query complexity, right? And this is sort of related to the sort of big question about, how much more powerful are quantum computers than deterministic computers, right? And this sort of looks at the question specifically in the setting of query complexity and, again, specifically for total functions. Cool. So before this work, this question was investigated by Nissan Szegedi, and Beals, Merman, Cleve, Moskin, de Wolf, which finally it was known that the deterministic query complexity of F is bounded above by the quantum query complexity of F to the 6th power. This work proves that result. It shows that the deterministic query complexity of F is bounded above by the quantum query complexity of F to the 4th power. So it improves a power 6 to a power 4 relationship. And this relationship is tight. There's an example due to Ambinas, Balotis, Belovsky, Santos, Motrovs, that where the deterministic query complexity is quantum query complexity to the 4th. Right. So in particular, this relationship cannot be improved upon. Cool. And one of the main ingredients in this relationship between the degree of between the deterministic query complexity of a function and the quantum query complexity of a function is this notion of degree. So I'll define this. So the idea of a degree of a Boolean function comes from the fact that every Boolean function can be represented exactly by a polynomial. Right? In particular, for every Boolean function, there exists a polynomial, so that if you feed the polynomial your input bits, the value of the polynomial is going to be the same as the value of the function. And it's maybe worth mentioning that the exponents of all of the variables in the polynomial are going to be 0 and 1 in the case of a Boolean function. Then we say that the degree of a Boolean function is just the degree of its polynomial representation. And one way you can kind of think about degree is that it's going to be a lower bound on the deterministic query complexity of F. So degree is often useful as sort of, say, a proxy for the deterministic query complexity of F. We can maybe do a quick example and look at the degree of OR. Right? OR is this function, again, that 0 if all the input bits are 0, or 1 otherwise. And it turns out that we can represent OR with this polynomial 1 minus the product from I equals 1 to n of 1 minus x of I. Right? In this case, if all the x of i's are 0, then the value of this product is going to be 1, and the value of the polynomial in the n is going to be 0. If any one of the x of i's is 1, then the value of this product is going to be it's going to be 0, and then the value of the final polynomial is going to be 1. This polynomial has degree n, so the degree of OR is going to be n. The second notion we're going to be using in this, we'll use in this proof is that of spectral sensitivity. So the spectral sensitivity of the Boolean function is the largest eigenvalue of the matrix A of F. I'm going to index my matrix by the rows and columns of my matrix by strings of 0s and 1s. Can maybe, if this is something you feel a little bit uncomfortable with, you can maybe think of this as, say, the binary representation, and there could be 0 indexing rather than 1 indexing. And this matrix is going to be defined as follows. A of F of x comma y is going to be equal to 1 if x and y differ in 1 coordinate and f of x is not equal to f of y, and it's going to be 0 otherwise. So you can think of A of F as the adjacency matrix of a subgraph of the hypercube. In particular, we're going to form this subgraph of the hypercube by putting all of the 0 inputs of our function f on one side and all of the one inputs of our function f on the other side, and only keeping those edges that go from a 0 input to a 1 input or vice versa. And if that edge goes from a 0 input to a 0 input or a 1 input to a 1 input, then we're going to remove those edges. And again, it will be nice to sort of look at the example of OR, the spectral sensitivity of OR. I have sort of a picture of what this looks like, as a subgraph of the hypercube in the case where we have OR on 3 input bits, right? And in particular, the all zeros function is the only 0 input, right? So we're going to be looking only at those edges that go from the all zeros function to, from the all zeros input to any other input. Right, so in particular, in the case of 3 inputs, we'll have an edge from 0, 0, 0 to 1, 0, 0, from 0, 0, 0 to 0, 1, 0, and 0, 0, 0 to 0, 0, 1. And in general, sort of the subgraph of the hypercube will end up looking at like the star graph. So in the adjacency matrix so in this case, A of OR, so the matrix we obtain is going to be this matrix, or I'm going to be deleting there are going to be a lot of 0 rows and 0 columns, so I'm going to be deleting those. What we'll get sort of in the end is this matrix that looks as follows. That first row is going to have a 0 and then a bunch of 1s. All other columns will have a 1 and then a bunch of 0s. And then we can compute the largest eigenvalue of this matrix is going to end up being square root of that. Cool, and it's worth mentioning that, so this idea of degree is something that is sort of well studied. But the idea of spectral sensitivity, it's sort of come up here and there, and it wasn't really useful in sort of a very important way until Huang used it in his proof of the sensitivity conjecture. So one way to sort of interpret our work also is it's going to show that spectral sensitivity is actually really useful in a lot of different contexts. Cool, so I'll give a quick proof overview of this proof that the degree of any function is bounded above by the quantum query complexity of f squared. Cool, so the first step is due to Huang, who showed that the degree of f is bounded above by the spectral sensitivity of f squared. What we show in this work is that the spectral sensitivity of f is bounded above by sort of this quantity you get from applying the spectral adversary method to f. And finally, Barnum, Sachs, and Seghetti show that when you apply this, the quantity you get from applying the spectral adversary method to f is bounded above by the quantum query complexity of f. Cool, and all of these combined end up showing that the degree of f is bounded above by the quantum query complexity of f squared. Cool, and I won't go into too much detail about sort of this quantity you get from applying the spectral adversary method to f. What I will mention is that it's also another quantity sort of related where based on sort of a matrix you obtain from the definition of f, and in particular, the proof that lambda of f is bounded above by SA of f is, I would say, relatively straightforward. Cool, now I'll mention how we can sort of get this relationship between the deterministic query complexity of f and the quantum query complexity of f. Cool, and the first step is due to Midrihanis, who showed that the deterministic query complexity of f is bounded above by the block sensitivity of f times the degree of f. Beals, Berman, Cleve, Mosca, DeWolf showed that the block sensitivity of f is bounded above by the quantum query complexity of f squared. And again, we show that the degree of f is bounded above by the quantum query complexity of f squared. Cool, so if we combine all of these together, we end up getting that the degree of f is bounded above by the quantum query complexity of f to the fourth. Finally, I'll mention briefly about how we can resolve the Aanderaa-Karp-Rosenberg conjecture at the quantum query complexity signing. Cool, so in particular, we show that the quantum query complexity of any non-trivial monotone graph property. Some examples include connectivity, k-clique, but on n vertices is omega of n. Cool, and this ends up being tight. So I'll mention first what I mean exactly by a non-trivial monotone graph property. So this is a graph property that sort of stays even if you add edges, right? So if you have a connected graph, adding edges will keep that graph connected. If you have a graph with a k-clique, adding edges will, that clique will still stay even if you add edges. Cool, and this is tight. You can think of the example of the problem where that asks, does there exist an edge in the graph? This is a problem almost like that of search. And this case, this requires omega of n quantum queries. Cool, so the proof proceeds as follows. The degree of any non-trivial monotone graph property is omega of n squared. This is due to Dodos and Khanna. And again, we show the degree of f is bounded above by the quantum query complexity of f squared. Cool, so again, if we combine both of these together, we get that the quantum query complexity of f of any quantum query complexity of any non-trivial monotone graph property is omega of n. One thing that's kind of remarkable about this result is that, basically this solves a quantum version of this problem. But in the randomized version of this problem, the best known lower bound for the randomized query complexity of any non-trivial monotone graph property at n vertices is n to the 4/3. And it's conjectured that the right answer to this is going to be omega of n squared. Well, so this is a situation where we know sort of the right answer for the quantum setting. But in the classical setting of randomized query complexity, we don't know sort of the right answer. We don't have a proof of what we think is sort of the right bound. Cool. So the next set of results uses the notion of approximate degree. So we'll go ahead and define this. So we say that a polynomial p epsilon approximates a Boolean function f if the absolute value of f of x minus p of x is bounded both by epsilon, and p of x is between 0 and 1 for all x and for all x that n 0, 1 to the end. But if x isn't a Boolean input, then we will allow the polynomial to sort of take on any value. The approximate degree of a Boolean function is the smallest degree of a polynomial that 1/3 approximates f. And one reason why the approximate degree of a function is so useful to think about is that Beal, Sperman, Cleve, Mosca, and DeWolf show that the approximate degree of a function is bounded above by the quantum query complexity of a function. Cool. So if you're someone like me who's still kind of getting their feet wet with quantum query complexity, you still are trying to kind of understand intuitively what is quantum query complexity. Well, what this result shows is that you can use the approximate degree as a proxy for quantum query complexity. So if you feel more comfortable thinking about the approximate degree of a function, you can just focus on that rather than thinking about the query complexity of a function. Cool, so again, it will be helpful to look at an example of OR. The approximate degree of OR is a little bit more complicated. So we can look at the case where there's two input bits, right? So we're looking at the OR of x1, comma x2. We can approximate this by the polynomial 1/3 plus 1/3 x1 plus 1/3 x2, right? This is because if x1 and x2 are both 0, the value is 1/3. If x1 or x2 is 1 and the other is 0, the value is going to be 2/3. If both x1 and x2 are 1, then the value of the polynomial is going to be 1. So in all cases, the value of the polynomial is at most 1/3 away from the actual value of OR of x1, x2. And the degree of this polynomial is 1. So we can say that OR on two inputs is has approximate degree of 1. In general, the approximate degree of OR is going to be theta squared root of n. One construction follows from Chebyshev polynomials. Another construction, if you're very familiar with, say, Grover's algorithm, and also this lower bound on the quantum query complexity of a function. Basically, this lower bound shows that if you have any quantum query algorithm, you can extract from that a polynomial. And that polynomial will have degree up to constant factors equal to the number of queries that the quantum query algorithm uses. So because Grover's algorithm uses square root of n queries, from Grover's algorithm, we can extract a polynomial of degree theta square root of n. Cool, so another major question is, what is the relationship between degree and the approximate degree of a function? And this was studied by Nissan Szegedy and Beal, Sperman, Cleve, Mosca, and DeWolf, and showed that for all total Boolean functions, the degree of a function f is bounded above by the approximate degree to the 6th power. What we show in this work is that for all total Boolean functions, the degree of a function is bounded above by the approximate degree squared. This relationship is tight. This is because the degree of OR is equal to n, the approximate degree of OR is equal to theta square root of n. I'll mention one application of this, and that is the approximate degree of read-once formulas. A read-once formula is a formula of and, or in that case, in which each variable appears exactly once. So I have here a diagram of an example of a read-once formula. We have an and of 3 ands of a bunch of variables and the or of those ands. Each variable appears exactly once in this formula, so this is a read-once formula. Cool. And one corollary of this result between the degree and the approximate degree of any Boolean function is that the approximate degree of any read-once formula on n variables is omega of square root of n. And this ends up being tight. The proof just follows from the fact that the degree of any read-once formula on n variables is n. The fact that this relationship is tight follows from the fact that we have quantum algorithms that can compute read-once formulas. So I'll give a quick proof overview of this result. Right, so we show that for all Boolean functions, the degree is bound above the approximate degree of f squared. And again, this proof is going to rely a lot on Huang's result. Huang showed that the degree of f is bounded above by lambda of f squared, the spectral sensitivity of f squared. And what we show is that the spectral sensitivity of f is bounded above by the approximate degree of f. Cool, so I'll give sort of a quick overview of the proof that spectral sensitivity of f is bounded above by the approximate degree of f. So the idea works as follows. The first thing is to notice is that if we look at the x comma y entry of our matrix A of f, this will end up being equal to 1 minus 2 of f of x minus 1 times 2 of f of y minus 1, as long as x and y differ in 1 quarter. Right? The reason why is that if x is not equal to f of y, this product, 2 of f of x minus 1 times 2 of f of y minus 1 is going to be equal to minus 1, and then the end will get 2. If they're equal, then this product will be equal to 1, and sort of the final value on the right-hand side of the equality will be 0. Cool. So using this fact, we get that 2 times a of f is equal to a of h minus this matrix we get by putting 2 minus 2 of f minus 1 along the diagonal of our matrix times a of h times, again, the matrix we get from putting 2 times f minus 1 on the diagonal of our matrix, where a of h is going to be the adjacency matrix for the hypercube. We can consider first a simple case where f is a parity function on d inputs. In this case, it actually turns out that a of h and this matrix a of h multiplied on both sides by this diagonal matrix actually have the same eigenvectors. And their eigenvalues don't differ by more than 2 times d. Right? In particular, both of these matrices will have parity functions as the eigenvectors. And sort of the fact that the second matrix also has parity functions as eigenvectors kind of follows from the fact that if you sort of take the coordinate-wise product of any 2 parity functions, you'll get another parity function. And then the last thing we can do is we can use this idea first to generalize to polynomials and then generalize to approximations. Cool. So just a few quick take-home messages. We show that the deterministic query complexity of f is bounded above by the quantum query complexity of f to the 4th for total functions f. We also show that the degree of f is bounded above by the approximate degree of f squared. And maybe it's worth mentioning that if you combine this with the lower bound for the quantum query complexity of f, that the approximate degree of f squared, that we also get another proof of the result that the degree of f is bounded above by the quantum query complexity of f squared. But I'll mention that this former proof method using the spectral adversary method is a little bit maybe more straightforward once we use sort of the pre-existing tools. Cool. And the last sort of take-home message is that spectral sensitivity is a really useful complexity measure. Right? It was used for both of these results, and it was also, of course, used in Huang's proof of the sensitivity conjecture. So there are a few sort of major open problems. The first open problem is, what is the relationship between R of f, randomized query complexity, which I didn't define, but in which case the queries are going to be randomized queries, and the quantum query complexity of f? And I think 2 talks before this one, there's this result that shows that there exists f such that our randomized query complexity of f is equal to omega of the quantum query complexity of f cubed due to Baha, Panzel, and Sinha, and Shurtstoff, Sturo, Zenku, and Wu. But maybe sort of the question here is, is the right power 3 or 4? Well, and the second major open problem is, what is the relationship between block sensitivity of f and lambda of f? Right, and in particular, can maybe the block sensitivity of f being equal to being upper bounded by lambda of f to the 4th due to Huang be improved? In our paper, we have this table of relationships and separations between complexity measures. So in particular, anything that any entry in white represents a relationship for which we know the optimal separation, and we have an example of that separation. But basically, anything in gray is an open problem, including the 2 open problems I mentioned. They're in this table as gray. But and basically any gray entry in this table is also an open problem. Cool, and that concludes my talk. Thank you for listening.